it's interesting. One thing that's kind of struck me straight away is you mentioned linked lists, and you've got it ringing in my head that we did a video on linked lists, and people were commenting, nobody ever uses linked lists in real life. Would you say they're used here because it's just for one or two elements here and there?
They're used here because it's a data structure that expands gracefully. In other words, we don't know when we create that original table how many items there are going to be in a particular use of a particular slot in the table. And so the linked list has the advantage that it grows very gracefully if something else, if it keeps going like this, the linked list adapts very nicely. This, changing the size of an array like this, is kind of a biggish operation. You don't want to do it very often, but adding a single element to a linked list is really easy. If it's a hash table, you could add it either at the end or you could add it at the beginning. It doesn't matter what the order is in that sense. So linked list actually makes a lot of sense for this context, and it's only singly linked list, which is the easy one. So because you don't have to go backwards, you're always just looking down to see whether something is there or not. So no, linked list is an absolutely useful data structure for this. And this is one of these things that's kind of intriguing, and perhaps the reason why I said that associative arrays are, if you're only going to have one data structure, it's the one to have. You can fake anything else with an associative array. So if that's your primitive operator, as it is in a language like awk, for example, then with that associative array, you can make any other kind of data structure that you want. It may be a little clunky, it may not run very fast, but it's perfectly fine. So for example, suppose, and here I am, let's call it an awk, I want to build an array whose indexes are the integers from 0 to whatever, just as we're used to. Well, gee, x of 0, that's a perfectly fine value. I would probably want to convert it to a string, and then x of 1 is a perfectly fine value, and so they're all there, no cost, because this is really x of 0, like that, right? So no problem at all in simulating ordinary indexed arrays in associative arrays, or with an associative array.
So this is like your Swiss Army knife of arrays, right?
It is the Swiss Army knife of data structures. You can build any darn thing you want with it. And like Swiss Army knives, it doesn't work perfectly for everything. If you want to go and kill people on the battlefield, Swiss Army knife is not quite right. But for this kind of thing, it's absolutely wonderful data structure.
We talked a lot about hashes and kind of the security world, and also kind of checking that things are what you think they are. Mm-hmm. Is this just the same? It's just a function, is it? It's
a function that takes some input, arbitrary thing. I've been talking as if it were a string of characters. Could be a URL, could be people's names, or postcodes, anything you want, and converts it into an integer in a particular range, 0 to something. And then from that, you can use that as a surrogate for the original, but you have to watch out for duplication. So if you have a lot of things, some of them are necessarily going to hash to the same value.
Yeah, because when things wrap round and round and round, you get these collisions, don't you?
That's right. If I've got 1,000,000 things and I want to hash them into 100 distinct values, something's going to give. But one of the things that happens in cryptographic kinds of things, where the hashing is more complicated, of course, is that you can't go backwards. Here's the hash. It's a number between 1 and 100. You have no idea which of the 1,000,000 things produced that hash. Although you could go and try the 1,000,000 things and see which one it was, but there's no guarantee that the particular one that you picked was also the one that somebody else had picked.